So let's look at the following example. We're gonna move this table a little bit. So we're gonna set up, I will point out, this in general, for a lot of volume questions, especially on exams, end up being just set up and do not evaluate the integral problems because the evaluation is just kind of gross. So make sure, especially on an exam, that you read the question carefully and only do the thing you're being asked to do and not too much. I'm going to write set up here, but we might actually evaluate this one, so we'll see. So we're going to set up the integral for the volume of the solid formed when the region bounded by y equal to x squared, x equal to 0, and y equal to x plus 2 in the first quadrant is revolved about, and the first part will be the x-axis. And I think it's a pretty good practice to, whenever you're doing a volume question like this, or I should say, whenever you're doing a volume of revolution, you're revolving some region around some axis, it is almost always the best idea to draw the region. You don't have to try and draw the 3D shape, but definitely drawing the region to revolving is going to help. So I'm just going to graph these three curves. So let's see here. So y equals x squared. Let's use some different colors here. Here's y equals x squared. And x equals 0 is our good old y-axis. And then y equals x plus 2 is a straight line. It's got a slope of 1, a y-intercept of 2. So it's going to be something like this. And you'll notice it was important that I specified that I only want the region in the first quadrant. Because if I hadn't said that, it could have been this region in the left over here or this region in the right over here. But we're definitely looking at this region here. And we're going around the x-axis. Welcome. So before we even do anything else, since our region isn't flush with the axis of rotation, that means we're going to have to be using the washer method, right? We're going to have an inner radius and an outer radius. We're going to be subtracting out a circle. You don't have to know that right off the bat, but it's kind of good to just think about what's going to happen. So I'm going to draw my little rectangle or my little strip, and it's always going to be perpendicular to the axis of rotation. So here, since my axis of rotation is horizontal, my strip should be vertical. It's going to look like this. And what I'm thinking about is when I rotate that strip around, what kind of shape I'm getting out. I don't think you have to draw this next part, but I like to draw it just to show everyone what's going on. If we rotate that strip around the axis of rotation, we're getting this sort of shape. We're getting a washer. And the volume of that washer, well, it's always the same thing. It's always the area of the big circle minus the area of the little circle times the thickness. So I usually write that out as pi times big R squared minus pi times little r squared, all times the thickness, which is the small change in x in this case, the dx. I'm thinking about this here, but that's just a small thickness of dx. And then we actually have to figure out what the larger and smaller radii are. The larger radius is the function for, so I actually want to be super explicit here because it's going to change in a minute. So the larger radius is the function that's further away from the axis of rotation. So sometimes that means the function on top, but not always. So we're going to be extra careful here. So in this case, yeah, the function that's on top, the red function here, is the one further away. So our outer radius is going to be y equal to x plus 2. And our inner radius is going to be y equal to x squared. So the volume of the washer is going to be pi times x plus 2 squared minus pi times x squared squared all times dx. And then our total volume, we're just adding up all the washers. We're going to say how far left and how far right did these washers go? Well, they clearly go as far left as 0 and as far right as wherever these two curves intersect. So I want to figure out where x squared is equal to, I didn't label this other one, x plus 2. You might, so a lot of times you can just guess what the answer is going to be. You might be able to guess that, oh, if x is 2, 2 plus 2 and 2 squared are both equal to 4. You might also be able to guess this one over here. If x is -1, -1 plus 2 is 1, and -1 squared is also 1. Or you could do the work of setting them equal to each other and saying, oh yeah, x squared equals x plus 2, bring everything to the left, factor, and get x minus 2 times x plus 1 equal to 0. So yeah, x is going to equal +2. You don't have to, but we almost always factor out the pi in front of the integral. And then you have your larger radius squared, so x plus 2 squared, minus your smaller radius squared, x squared squared. I know x squared squared is x to the 4th, but if I'm only setting it up, I really actually want to write it as whatever the inner radius is, quantity squared, even if it's a really easy simplification. So I would really leave it like this. I don't think there's any point in simplifying it if you're just asked to set it up. I think you're doing yourself a disservice if you simplify it, because you're not, the person grading it isn't going to see the thing they're looking for, which is the function squared minus the other function squared. Yeah, all right. Questions about this one? If you were going to integrate this, I'll just point out, you would want to simplify it. So I'm not going to finish this off, but if we were going to integrate this, we would rewrite it as pi times the integral from 0 to 2, and then you'd have x squared plus 4x plus 4 minus x to the 4th. And then you have to differentiate each thing and plug in 2 and plug in 0 and subtract. When you're finding a volume, you should always get a positive answer. So if you somehow got a negative answer, you need to go back and look at, maybe you subtracted the wrong order or something, but it's probably subtracting the function in the wrong order. All right, let's look at a worse version of this problem. Worse is maybe not the right word, but a less nice version. No, it's worse. There's no getting around it. So let's rotate now around the y-axis. Like I was saying on Tuesday, if your axis is horizontal like it was before, you're always going to be integrating with respect to x. If your axis is vertical like it's going to be in this problem, you're going to be integrating with respect to y. Another way to see that is that your strip that you're going to draw is always perpendicular to your axis of rotation. I should leave myself more on the left here. So I'm going to draw the same little region, kind of. It's going to look vaguely like this. I don't really care about getting it perfect. Cool. There's my region, and we've got some points here. That's the point 0, 2. This is y equals x plus 2. This is y equals x squared. That's the point 2, 4. But there's a problem here. And the problem here is that when I draw my horizontal strip that's perpendicular to my axis of rotation, depending on how high or low I draw it, my left-hand boundary changes. So if I draw it down here, my left-hand boundary is x equals 0. My right-hand boundary is y equals x squared. If I draw it up here, my left-hand boundary is y equals x plus 2. My right-hand boundary is y equals x squared. That means I have to use 2 integrals. There's no other way to do it. So we're going to have to break this up at the y value where things change. So right there, that place where we're breaking things up is going to be y equal to 2. So the first integral is going to be the integral from 0 to 2. And the second integral is going to be the integral from y equals 2 to y equals 4. Questions?
Can we just do like vertical strip?
No, we can't. That's a really good question. And the reason why we can't, so I will point out, if you were in 21B, you would learn the shell method, which is where you can do a volume of revolution where your strip is parallel to your axis of rotation. But we only have the ability in this class to, or we only get taught the disk/washer method, which requires that the thing we're rotating is perpendicular to the axis of rotation. So no, we really cannot. So for this lower part here, when I rotate this little shape around here, what I'm going to get is I'm going to get a disk. And the volume of this little disk is going to be equal to pi times the radius squared times the thickness, which is dy. And for this part up here, when I rotate this part around, let's use a different color, James. I'll just go up instead of going down. When I rotate that part around, I'm going to get a washer. But the problem is, if I were to draw my strip vertically, like I would like to, the shape I get isn't a disc or a washer, where it's actually, I'm sorry, it doesn't look that dissimilar, but it's a totally different process. It's called a cylinder, and it's a cylindrical shell that we get, and the volume equation is different. And we don't talk about that here in this class. So no, we're stuck, unfortunately, using two integrals here. I agree. I would much rather use one integral, which we could do if we knew the shell method. But that's not what we've got. So let's do the bottom part first. So the bottom volume, we're going to get by doing, so it's going to be the volume of our disk. So that's going to be pi times, what's my radius of this disk here? What's my outer function? I guess the outer is not the right word here because there isn't an inner function. What's the function that's bounding the right-hand side of the disk? That's the left-hand side. Right, y equals x squared, but what variable are we integrating with respect to? Y. So instead of doing y equals x squared, we have to say that x is equal to the positive square root of y, because we're on the right-hand side. If it was the left-hand side of the parabola over here, it'd be x equal to the negative square root of y. So it's going to be pi times the square root of y squared times dy. And then we're going to integrate that from as low as 0 to as high as 2. And then the top part volume, then we're going to have to use the washer method. So for our outer radius, well, our outer radius is still the same function, right? It's still this parabola, which is we're thinking of as x equal to the square root of y. So it's going to be pi times the square root of y squared. That's my outer area, minus pi times the inner function squared. My inner function, well, the boundary is the line y equals x plus 2. So if I solve for x, it's going to be x equal to y minus 2. And then we integrate all of that from as low as y equals 2 to as high as y equals 4. And don't forget the dy. Questions, comments, concerns? This one actually, neither of these are that terrible to integrate, because the square root of y squared is just y, so it's fairly straightforward. Most of these volume questions are usually not too terrible as far as the method of integration. They're usually either pretty straightforward, like just powers of your variable, or maybe you have a small u sub, occasionally integration by parts, but usually nothing more terrible than that. This bottom one also pi times y, and this is pi times, you can multiply this out. It's not too bad. Let's do one more with this one. What if I want to rotate around the line? Sure, let's do that. Y equal to 5. Question, Jen. Add what? Oh yeah, sorry. Yes. You give fair point. Yeah. So then my final, you do this. Yes. You would add these together. Add together for the total volume. Yes, thank you. I should have mentioned that. So if I want to rotate around the line y equals 5, well, again, I like to draw the pic, sorry, I just find it helpful. Fun fact, you should never be rotating around a line that crosses through your area. That's usually just a mistake, because then the whole thing rotates on itself and it's kind of just not really sensible. I'm gonna draw this again. So there's our region with the same points, 0, 2, and 2, 4. Oh, I definitely made, it's not a mistake, just I should have drawn this differently, but oh well. And here's the line y equal to 5. We're rotating around that line. Well, what kind of strip should I draw? Should it be vertical or horizontal? I'm rotating around this horizontal line. So my strip should be perpendicular to it, so it should be vertical. I think what some of you might have been guessing horizontal, because I said if we're rotating around the y-axis, it should be horizontal. And now we're rotating around y equals 5, which is parallel to the x-axis, not to the y-axis. So there's my strip. And now if we're rotating around this, my outer radius is going to be that. The distance from to the function that's further away from the axis of rotation, and the inner radius is going to be this. The distance to the closer function. Okay, so let's see here. Let's see if I get the words out of my mouth. Let's just write the volume of our washer before we do the integration here. So the volume of just our washer, again, very, very generally, it's going to be pi times, I'm going to factor out the pi here and say it's your large radius squared minus your small radius squared times your thickness, which is dx. Technically, it doesn't matter which order you subtract things in here, but I would like to do it the most right way because we should be the most right we can be. So if I want to find this large radius here, remembering that the bottom function here is y equal to x squared, and this top function is y equal to x plus 2. The large radius is the difference between y equals 5 and y equals x squared. And I should be subtracting it as 5 minus x squared instead of x squared minus 5. Technically, both would be correct, but it should really be the bigger thing minus the smaller thing. And 5 is definitely above x squared, so 5 is the larger y value. So we're going to write this as pi times my large radius, which is 5 minus x squared, minus my smaller radius, which is going to be 5 minus x plus 2. Squared. So whenever you're finding these radii, it's always the difference between your function and your axis of rotation, which is what we've been doing this whole time. It's just that our axis of rotation up until now has always been either y equals 0 or x equals 0. So the difference, we didn't need to subtract off the 0 because it wasn't going to change anything. But here, it does matter. So then, if I want to find the total volume, if I want to set up the integral for the total volume, it's going to be pi times the integral from, well, my strips still go as far left as 0 and as far right as 2. That's the integral from 0 to 2 of this whole thing. 5 minus x squared squared minus 5 minus x plus 2 in parentheses squared. Which again wouldn't be the worst thing ever to integrate, but it's not nice. Like if you multiply this whole thing out, it gets a little bit gnarly to, you have like 3 or 4 or 5 terms, and you have to integrate each of them, and you got weird fractions. It's just not very convenient. So I feel like this is a good moment for me to have you all set one up. So I want you to try setting up the same integral, but now we're going to rotate around the line y equal to -2. Yeah, question, Jeff.
So this how we found with our smaller.
Uh-huh.
For B, could we do the same thing and not make two different intervals and just make one?
We cannot. And the reason why is because so in this, so the difference between this rotation around the y=5 and this rotation around the y-axis here is that for this one down here, no matter where I drew my strip, the boundary functions never change, right? I could draw it all the way over here or all the way over here, and no matter where I draw it, the bottom boundary is always y=x², and the top boundary is always y=x+2. On the other hand, over here, first of all, I'm rotating around the y-axis, so I have to draw horizontal strips. And then, since I'm drawing horizontal strips, I don't have a choice. If I draw my strip down here, the left boundary is x=0. The right boundary is x=√y. But if I go up too high, like right here, my left boundary changes. Now the left boundary is this other function. There's nothing I can do about that. It's just, that is my new function. It totally changes the type of interval we're doing, right? The bottom is just a disk method, whereas the top part is a washer method. So there's really no getting around it. That's why, I'll say one more thing. That's why I think it's really important to draw these strips, because if you draw them, it helps you see, oh, do I have to break it up into two integrals, or is it the same thing no matter which way I draw it? So try setting up the one for rotating around y equals -2. And I will draw the region one more time. You really feel. Okay, yeah, you guys all look like you're ready to say words, so let's say words. So, similar idea. Again, we know, well, actually, I should back up for a second. I know I've already labeled it in a way that makes it obvious, but is this going to be a disk or a washer? Definitely going to be a washer, because our region, well, it's not even touching the axis of rotation, but more importantly, it's not flush with the axis of rotation. So here, definitely washer method. The volume of a washer, as is, I know it gets old, but I think you should write this every time. The volume of a washer is area of the big circle minus area of the little circle, all times the thickness. Makes it easy to know what's going on. And then my big, and then we can factor out pi. My large radius, I didn't label my functions here. There's y=x+2. Here's y=x². So unlike the previous one, where my large radius was 5 - x², now my large radius is going to be x+2 minus -2. Which feels a little silly to write minus -2. And then we're squaring that. And my smaller radius is x² minus -2. I might simplify that a little bit if I was actually writing it out, because it just looks terrible. So if I was going to write out my total volume, it's going to be the integral, still from 0 to 2, put the pi out front, x+2 plus another 2 is x+4 squared, and x² minus -2 is x² plus 4 squared. Oh, I forgot the dx up here, sorry. So that's how I'd probably write it, because this feels really silly to write minus -2 a bunch of times. Yes.
Why does the second one become x² plus 4 if you're?
Oh, because I made a mistake. Thank you. +2. Still +2. I don't know why I said +4. So setting these up, can be kind of tedious, but again, I think if you draw the picture of the region, draw your axis of rotation, and draw your perpendicular strip, it's not too terrible to figure out what's going on after that. Yeah, let's look at a different shape. But questions about anything I said so far? Figure out a different shape. Let's go back to that one. Sure. Yeah, sure. Okay, let's look over here. Oh, I know. Yeah, we'll do one of my favorite examples. Let's do the following. Let's find the volume of solid formed by revolving. A lot of the times people don't write these words, just like, here's the boundaries revolving around this axis, right? You don't always need all these words, but right, this kind of feels like, yes, okay, get to the point. Find the volume of the solid formed by revolving the region bounded by y equal to the square root of x, y equal to 6 minus x, and y equal to 0 around the y-axis. First step, draw the graphs of the things. They don't have to be perfect, just have to be approximately the right kind of shape. So we know that y equals the square root of x has the general nice square root shape. It looks something like this. Y equal to 6 minus x is a line going down from left to right. It's got a y-intercept of 6 and an x-intercept of 6. So it's going to look something like this. And y equals 0 is which axis? The x-axis. So here's my y equals 0. Okay, so it's really, really easy to make the mistake of getting the wrong region here. It would be really easy to accidentally grab this region over here because it looks like, oh, it's bounded by some things. But this region here is bounded by the y-axis, which we did not say was one of our boundaries, right? This y-axis is x equal to 0. So we're looking at this region here, bounded by the three things it's bounded by. Y equals root x, y equals 6, y equals 0, and y equals 6 minus x. And then revolving around the y-axis. So I'm going to draw my strip, which is going to have to be a horizontal strip to be perpendicular to the axis of rotation. And when you draw your strip, do yourself a favor. Don't draw it at the very ends of the region. Like, don't draw it at the bottom or the top or the left or the right. Sorry, left or the right. Draw it in the middle somewhere. Because when you draw it in the middle, you're going to be able to answer the question, is your strip touching the axis of rotation? Is it? No. So we know we have to use what method? The washer method. If it was touching the axis of rotation, no matter where, like, on the other hand, if I was going around the x-axis here, no matter where I drew my vertical strip, it would always be touching the x-axis. And that would tell me, oh, it's got to be the disk method. I'll also point out that if we went on the x-axis here, how many integrals would we have to use? We have to use 2. If we went on, because from there to here, right, our top function would be y equals root x, but then from here to there, our top function would be y equals 6 minus x. So there's no getting around it. But we're not doing that yet. So we're going to do this other. Yeah. We'll probably do it the other way too. Or at least we'll set it up. We're actually going to do this one. So let's find the volume of our washer. And every time, pi times the big radius squared minus the little radius squared times your thickness, which is dy. I do think it's worthwhile to do what I like to do, which is to kind of say, okay, cool. Here's my larger radius. And here's my smaller radius. Like I like to draw that in there. It just helps me figure out what's going on. My larger radius is the right function here, but we can't do it in terms of x, so it's not going to be 6 minus x. We need to solve this and say, great, y equals 6 minus x is going to be x plus y equals 6, or x equals 6 minus y. Occasionally it does happen that it looks like you just interchange x and y. That's not normally true, but it is true for this particular function. So we're going to get pi times our outer radius, which is 6 minus y squared. And then our inner radius is y equals root x, which becomes x equal to y squared. So minus y squared squared. Outer radius squared, inner radius squared. Now we're going to integrate. So we're going to find the total volume. Going to be pi times the integral from, we'll figure that out in a second. I am going to simplify this here. So instead of writing 6 minus y quantity squared, I'm going to write 36 minus 12y plus y squared minus y to the 4th. I know my lower limit of integration. That rectangle goes as low as y equal to 0. My upper limit of integration we haven't found yet. I feel like I see a question on your face.
Yeah, I set it up a little
Okay,
differently and I'm not sure.
Sure.
So what I do is I draw out the washer.
that's cool.
And I put
Yeah.
like x equals 0 in the middle, and then on each line I would do like x equals y squared, and then I can like visualize where the big R is. So like I wrote like little r as 0 minus y squared.
Sure. So I will say that won't end up being wrong
Oh.
because you're going to end up squaring it. Right? Because you're going to get 0 minus y squared squared.
Okay, because I did it for the last problem too.
Right. Right. It'll work out, but the thing is, technically, if you write 0 minus y squared, technically you're saying your little radius is negative. Because y squared is positive and 0 minus y squared is a negative number. When you square it, it tends to be okay. But really, when you're subtracting things to find either your radius, either big or little, it should always be right minus left. So in this case, my right thing is y squared. I should say my right thing is x equals y squared, and my left thing is x equals 0 versus 0 minus y squared. So right minus left if we're doing it in terms of y, top minus bottom if we're doing it in terms of x. So like in the previous one, right over here, right, when we were finding our large radius, we did the top thing, y equals x plus 2, minus the bottom thing, y equals negative 2. X plus 2 minus negative 2. If you had flipped that subtraction, it would still work out. Because whether this quantity is positive or negative, you're going to square it, which is going to make it end up being positive.
Okay.
But it's better to do it the way I do
Okay.
it. Better is maybe not the right word. It just feels better to me. I'll admit it's a personal bias that I have that I like to write it the way that's technically where the radius is positive, but it really actually doesn't matter. So as long as the Dell is cool with it, you should be fine either way. But you might want to double check that I imagine he might be a stickler for that as well. So upper limit of integration. We got to find the y value here. Now, here's the thing about a lot of these problems. A lot of them are set up to not suck. So while you could set root x equal to 6 minus x and then solve, you could also just guess good candidates. Like things that are easy to take the square root of. Like, okay, if x is 0, y is 0, y is, okay, it's not 0 obviously, but we start off, and then we try x equal to 1. The square root of 1 is 1, 6 minus 1 is 5. Okay, it's not 1. We try x equal to 4. The square root of 4 is 2. 6 minus 4 is, oh, it's also 2. So you can also sometimes just guess what the point's going to be. Sometimes you have to guess, especially if there's like a natural log involved. Occasionally you might have to guess it. But I will also say if you did set them equal to each other, if you set the square root of x equal to 6 minus x, and then square both sides, you'd have x equal to 36 minus 12x plus x squared. And then if you brought the negative x over, you have 0 equal to x squared minus 13x plus 36, which definitely does factor as x minus 9 times x minus 4. So they do intersect at 4. And if you drew the bottom half of this parabola here, they would also intersect when x is 9 and y is negative 3. But we don't care about that part. So definitely a y equal to 2 up there. Right? X is 4, but we want the y value, which is 2. And I said we were going to do this one, so I guess we'll do it. So integrating this, it's kind of gross, but it's not that gross. So you're going to get, let's see, 36y minus 12y squared over 2, which is 6y squared, plus y cubed over 3, minus y to the 5th over 5. Evaluate from 0 to 2. Do a quick check before I plug in. If I were to plug in 0, every term would be 0. So I'm not going to worry about that. But do check, because occasionally, if you have like an e to the y or a cosine of y, those things, when you plug in 0, you don't get back 0. So make sure, if you're thinking you plug in 0 and you get 0, do a quick double check. But if I plug in 2, I'm going to get pi times, let's see, 36 times 2 is 72. 6 times 4 is 24. 2 cubed over 3 is 8 over 3. 2 to the 5th over 5 is 32 over 5. And I find no good reason to simplify this further. So that's where we're going to leave it. That's where you should leave a problem like this on an exam. Even if he says you should simplify it fully, you should stop there. And then if you have more time at the end of your exam, then come back and finish simplifying that. But don't spend your time simplifying that. Nobody cares really about your ability to add or subtract fractions that much. Like, yes, we care a little bit, but we care much more that you were able to do the integration or the other things you're actually learning about in this class. Cool. Should we do the other way? Yes, we should. Okay, so we'll go around the x-axis and then we'll see what we want to do. So going around the x-axis. Shape it like this. Just kind of drawing it again. Then I've got this point here, which is 4, 2. This was y equal to the square root of x. This was y equal to 6 minus x. That point there would be 6, 0. And now we're going to break this up into 2 integrals. So from 0 to 4, we're going to draw a vertical strip. I should maybe be a little more circular. So let's rotate this region around the x-axis. Let me write the words. Rotate the same region around the, x-axis. So let's write the volume of each disk. So our left disk, the volume of that disk is going to be, well, again, for just a disk, when we know it's a disk because our region is flush with the axis of rotation, it's just pi times your radius squared times your thickness, which is dx. In this case, our radius is just the height of the function, which is the square root of x. So we get pi times the square root of x squared times dx. And that's going to be on the interval from 0 to 4. Like, I don't know this light here. Is that better? A little bit? Okay. I can get it dark. It's all right. I can always turn on that light here. Nope, I just turned it off. Sorry. Okay. And then the right disk. Well, again, same idea. We've got this strip here. And same idea. The volume of that right disk is going to be pi times your radius squared times dx, which in this case is going to be pi times 6 minus x squared times dx on the interval from 4 to 6. So the total volume is going to be those two intervals added together. It's going to equal the I should say pi times the integral from 0 to 4 of the square root of x squared dx plus pi times the integral from 4 to 6 of 6 minus x squared dx. Yeah.
This flow continues over one, you're supposed to break it up into two intervals.
Sure.
One goes over one.
So the not helpful answer is whenever you have to. But right, but really the point is like, we don't do this unless we have to. So the way you know that you have to break it up is if you look at your region, so this is where the whole drawing of the vertical or horizontal strip thing comes into play. So look back at the previous one for just a moment here. If I can. No matter where I drew this horizontal strip, whether I drew it very, very low, or in the middle, or very, very high, the right-hand boundary was always this red curve. The left-hand boundary was always this black curve. On the other hand, in the same shape down here, when I draw a vertical strip, well, no matter where I draw the vertical strip, the bottom boundary is always y equals 0, but the top boundary changes, right? Between 0 and 4, the top boundary is y equal to the square root of x, whereas between 4 and 6, the top boundary is y equal to 6 minus x. And so if one of the boundary or both of the boundary functions changes midway through, that's where you have to break it up into multiple intervals. And yeah, it's kind of not another good way of saying that. Yeah, we'll do one more thing about this. I feel like it's not another question about this. No? Okay, cool. And I guess we could calculate this, although it doesn't feel like it's super necessary. If we wanted to calculate it, it'd be pi times the integral from 0 to 4 of x plus pi times the integral from 4 to 6 of 36 minus 12x plus x squared. And then it's just, you all know how to do this. I'm going to factor out the pi completely and say it's x squared over 2 evaluated from 0 to 4 plus the 36x minus 12x squared over 2 plus x cubed over 3 evaluated from 4 to 6. And then you can plug in numbers and get numbers. Yeah, sometimes. Let's just not, but let's just leave it right there. All right, so here's a question I think that is worth thinking about for a minute. We're still gonna look at the same region for just one more example. We're not really gonna do the whole thing, but I should say, we're gonna kind of look at the same region. I'm gonna draw the same region one more time. So once again, one more time. Do all the labeling using different colors. There's my y equals 6 minus x. And here's my y equal to the square root of x. And here's the point 4 comma 2. And here's the point 6 comma 0 and 0 comma 6. But now we're going to change it up a little bit. We're going to instead say, let's say that the region is not bounded by these two functions and the x-axis, but these two functions and the y-axis. So our region is bounded by y equals 6 minus x, y equals the square root of x, and x equal to 0, which is the y-axis. So I want all of you to set up the integrals, plural, for revolution about the y-axis. I want you to draw your horizontal strips and see that depending on where you draw it, you get a different right-hand boundary function for, again, this region here. Give you a few minutes to work on that. Plus, here, not plugged in. All right, let's take a look. So I've drawn little horizontal strips, and they had to be horizontal because they have to be perpendicular to the axis of rotation, and the axis of rotation is vertical. And then we see that if we draw it lower than the line y equals 2, the right-hand boundary is y equal root x or x equals y squared. If we draw it above the line y equal 2, our right-hand boundary is y equal to 6 minus x or x equal to 6 minus y. So if we're going to set up the integrals for the volume of this region that we're rotating around the y-axis here, then we're going to say, well, the volume is going to be the first integral is going to go from a lower y value of 0 to an upper y value of 2. My outer radius, actually, I should say my only radius, because they're both disk method problems. I could say my outer radius is x equal to y squared. And my inner radius is 0. That's technically true, which is really what makes the washer method the same as the disk method. It's just the disk method is the washer method where the inner radius is 0. And then the second integral is going to be pi times the integral from a y value of 2 to a y value of 6. And my radius, which again is just the length of my strip here, is going to be my right-hand boundary, which is x equal to 6 minus y. So it's that 6 minus y radius squared. Y. And that's fully how we set this up. And hopefully you're starting to see that, oh yeah, we have to use two integrals here because there's no way we can draw a horizontal strip that always has the same right-hand boundary in this particular case. Most of the time with volumes of revolution, they're usually just one integral, but occasionally you will have one where you have to break it up as two integrals. More than that is very atypical. Not that it's impossible, just no one's going to ask about it. I think we pretty much said all we need to say about volume. Not that we couldn't say more, right? I could talk about volume for another half hour if I really wanted to. Certainly, I think it would be a good idea for all of you on your own, when you have a moment, to write the integral, single integral for the volume we get by revolving this region around, take your pick, the x-axis, the line y equal to 9, or the line y equal to -2. All those would be good practice. They will all be single integrals. They will all be the washer method, and you'll have varying radii lengths depending on which one you pick. It's really all. I'll point out that each of these will all be pi times some integral from 0 to 4 of some outer radius squared times some minus some inner radius squared. It just depends on which one you do, because it will make your radii different. But I would be very, very surprised if you were not asked to do at least something like this on an exam, to rotate around an atypical non-standard axis, which isn't just the y-axis or the x-axis. All right. Let us move on, since, right, I'm not going to see you until Tuesday, and you're going to have 2 classes before then, where you're probably going to start talking about differential equations in chapter 7. Yeah. Where? Here? 0 to 4. Right, so right, because if we drew vertical strips or 5, no, you're good. If we drew vertical strips, they would go as far left as x equals 0 and as far right as x equals 4. That's why the boundary is. No matter which vertical axis, sorry, no matter which horizontal axis we rotated around, right? The region is still bounded by x going from 0 to 4, and you kind of have no other choice. And so that's actually something worth noting, is that no matter what axis you rotate things around, as long as you're still doing things in terms of x, the limits of integration are never going to change. Same thing is true if you're doing things in terms of y. Limits of integration are never going to change, whether it's, you know, the y-axis or the line x equals 7 or the line x equals -3. Right? You're still going to have the same region, just being revolved around different axes. All right, let's take some time to talk about differential equation. And although I'm not going to write these next words down, I'm going to say them. We'll write them out later. But eventually, what we'll see is that when a differential equation is an equation that involves a function and one or more of its derivatives. That's what makes a differential equation. But we'll kind of build it up. So let's harken back to the days of 17A. And I'll ask you to recall something that we did. I don't remember when we did it in 17A, but we definitely did it. So if you have some n of t, where n is like the population at time t, and it's equal to, let's say, 3 times 2 to the t, we can think of this as a sequence, right? We did some sequences back in 17A. I know, don't worry, we're not going to be doing sequences again, but I'll point out, you can think of this as a sequence that describes exponential growth, which I hope is somewhat obvious, because literally we have an exponential function, 2 raised to the power of t. And we could certainly, you know, find some values for t and n of t at time 0. N of 0 would be 3 times 2 to the 0. At time 1, n of 1 would be 3 times 2 to the first. Time 2, you get 3 times 2 squared. Oh, like every time we're just doubling the population. Right? Whenever you increase t by 1, whatever, right, t could be hours or days or years or whatever unit of time we decide it is. But every time our unit of time increases by 1, the population just doubles, right? 3 times 2 to the third is 3 times 8, which is 24. And so on and so on. But I also want to point out, also, this sequence could have been written as a recursive sequence. And I'll remind you, a recursive sequence is just a sequence where to find essentially the next value, you have to know the previous value. So in this case, it looks like every subsequent value is twice the previous value. So we could write it as the next value of the population, n at t plus 1, is equal to twice the previous value of the population. Now, when you have a recursive sequence, you also typically need to state what the initial condition is. So we would also say, and we know that n of 0 is equal to 3. So then if we wanted to, you'd be like, okay, well then if n of 0 is equal to 3, n sub 0 plus 1 is equal to 2 times n sub 0, which is 2 times 3, which is 6. And then n sub 1 plus 1 is equal to 2 times n sub 1, which is 2 times 6, which is 12, and so on and so on. If, instead of thinking of this function as being kind of discrete, right, where you're saying time can only be these integer values and the output's going to be these integer values, if we thought of this function as being continuous instead, we could describe this recursive relationship in a slightly different way. We could say, as a continuous function, I'll just remind you that you know what exponential functions look like. You've graphed them. You know what e to the x looks like. You know what 2 to the x looks like. They are continuous functions, right? They have that nice exponential shape. Did I ever talk about the right-hand thing with exponential functions? My hand is never the best for this because I have a number of years. I have a few more years than you all do. But if you look at your right hand, you can kind of see here, there's a nice exponential curve, e to the x. And additionally, over here, over your thumb, there's a nice natural log of x curve. You make sure you look at your right hand, though. You look at your left hand, it's e to the negative x and the natural log of negative x, which is less helpful. So you look at your right hand, you have those curves on there. But I do want to point out, e to the x is a nice exponential continuous function, as is any exponential function with a positive base. We don't really think about negative bases, so yeah. Get back out. Good job. So as a continuous function, we can describe this relationship with a differential equation. And that differential equation is the following: that the rate of change of our population n is 2 times the population size, where the initial population is still 3. It's kind of cool. So what we're kind of saying here is that at time 0, when the population is, yeah, I guess I gotta make sure this is. Let me think about one thing. Yeah, that's fine. Yeah. Sure. I'm gonna leave it there. It can be a little more complicated than that, but we don't want to get too detailed right now. So this is the idea. Sorry, I feel like I'm glossing over something. I just want to make sure I'm really not. All right. One moment, please, while I think about this for just a second. That's kind of dicey. But it's close enough. Okay, we'll let it go. I'll try my best to let it go here. So this is an example of a differential equation. Not quite right, but I'm going. Yeah, it's not the point, James. The point is not to be right. The point is to show the thing. So what makes this a differential equation is the fact that there is a function n, right? Or you can write n of t, we just write n, and one or more of its derivatives. And we have some names for these, which are kind of annoying, but usually people like to talk about them. These names are not super important, except for the times when your teacher asks you on the exam, what kind of differential equation is this? Is it this, or this? So we'll talk about them for a second. So we have three types of differential equations. We have, I should let see, types of, we usually abbreviate differential equations as diff EQs. Three types of diff EQs. Autonomous. What autonomous means is that it doesn't matter what time it is, the relationship still has kind of the same thing going on. And actually, this first example is an example of an autonomous differential equation because the rate of change of the population size doesn't depend on time. It's equal to a function of just the population size itself. I will also point out that this is exactly the kind of differential equation that leads to exponential growth. Because what we're saying here is the rate of change of the population is 2 times the population size. So if the population gets bigger, the population starts growing faster, and then it gets bigger, and then it grows faster. And so if you have a population whose rate of change is a multiple of the population size, that is always meaning that we have exponential growth. So autonomous means no time in our equation. Except for, of course, the dt down there. You have to have that dt down there because you have to have a derivative. Then you can have kind of the opposite of that, which is pure time. Meaning your derivative only depends on time and it does not depend on the population size. So something like dn dt equal to 3t squared. So no function, which we're calling n, but you can call anything, right? N or y or f in our equation. And then thirdly, the book uses the term non-autonomous. So basically, if it's not autonomous and it's not pure time, we call it non-autonomous. So basically, that's where your derivative can depend on time and or population size. So we could say like dn dt equals 2n plus 3t squared. This is non-autonomous because it's not just depending on n. Technically, pure times are also non-autonomous because they're not depending on just n. But if it's pure time, we label it as pure time. Where if it's time and the function, we label it as non-autonomous. Again, knowing these names is, in my opinion, not super duper important. But again, it might be if your teacher decides to test you on it. So only important in that way. The more important thing about differential equations is how we classify them so that we can solve them. So classifications. And here's what I would say. There's a few different words we use here. So one word we're going to use is the word order. The order just means kind of like the degree of a polynomial. Like if I said my polynomial was x to the fourth plus 2x squared plus 1, you would say that's a 4th degree polynomial because the highest power of x is 4. In a similar way, the highest derivative is the order of the differential equation. So if you have a second derivative, it's a second order differential equation. Some examples. So here's one example. Here's an example of a first order linear differential equation. So let's write it down as, we'll say dn dt equal to 2 times n plus 3, or another example, dy dt plus, sure, t squared times y equals natural log of t. All right. So both of these are first order because the highest derivative I have is the first derivative. dn dt, dy dt, I also could have written y prime here instead if you prefer. Okay. What about the linear word I used? Well, the linearity specifically applies to the name of the function. So in this first equation, n is my function, and looking at the not derivative parts, but just the other parts, the only power of n I have is n to the first. So that part there is the thing that's making it linear. Is if you only have an n to the first. If you had an n squared or a square root of n or any other thing involving n, like sine of n or the square or natural log of n, it wouldn't be linear. Same deal over here. In the second example, y is my function. It's only got the first derivative of y, and then every other instance of y is y to the first power. So also linear because of the y right there. It doesn't matter that t is to some other power, there's a natural log of t. T is not the thing we care about. Y is the thing we care about. The function is the thing we care about. We're talking about differential equations. The function is the thing that's important, whether it's y or f of x or n of t or whatever. Okay, a few more things here. Yeah. So here's a first order quadratic differential equation. So let me ask you all a question. How could I easily change this one I just wrote here so that it's now a first order quadratic? What would I have to change? What could I change?
Could you just change the gradient to outer length?
Yep. Yeah, exactly. So I can write it as dn dt equal to 2 times n squared plus 3. It's still first order, but now the power of n is to the second power, so it's a quadratic in that variable instead of being a linear thing. Or it could be something like y prime plus x to the 7th times y squared plus x to the 5th times y equal to x squared. Also, quadratic first order linear, or sorry, not linear, first order quadratic differential equation, because the function y, I only have its first derivative, and I only have a second power or a first power of y. Nothing higher, nothing weird. And then we'll do one more, just kind of, so we had a second order linear differential equation. It could be something like n double prime of t plus n prime of t plus 2n equal to t cubed plus 7. My derivatives are a first derivative and a second derivative, so that's what's making it second order. But my only powers of n are still n to the first, making it linear. Another example could be something like d squared y dx squared equal to -5 times y. Second order because it's a second derivative of y, linear because you only have a y to the first. And as far as we're concerned, if we're talking about trying to solve these things eventually, the only ones we really care about are the first order linear ones. There's a very special way for solving first order linear. That's not true. That's not the so we either care that they're first order linear, or there's something that we call step linear, which we'll get to in a bit. I don't love all this. Sure. How much do I want to say here? How much time? 10 minutes? Okay. All right, let's look at this. So we're not going to solve any differential equations today. We've kind of Well, that's not true. You totally could solve a differential equation. You solved differential equations before. In fact, you've spent a lot of this quarter already solving differential equations. Like, you can definitely solve the differential equation dy dx equal to x squared with y of 0 equal to 5. You know how to solve this. If the derivative is equal to x squared, you can find the function by differentiating. So the solution here is to first, we're going to separate the variables. So when you're separating variables, it means you want all of the y's on one side, all of the x's on the other side. So I'm going to have dy on the left, x squared times dx on the right. And your d whatever, your dy or dx, has to not be in the denominator. So that dx, we multiply both sides by dx up on the right. And then you integrate both sides. The integral of 1 dy is just y. The integral of x squared is x cubed over 3 plus c. And then we use our initial condition to solve for c. So plugging that in, we say, okay, cool. Y is 5, x is 0. And we end up getting c equal to 5. So then our final solution here is going to be y equal to x cubed over 3 plus 5. Its derivative is certainly equal to x squared, and the initial condition is that when you plug in 0 for x, you get 5 for y. So that's a very, very basic example of solving a differential equation. And I will tell you, most of the differential equations we see are solved via this method of separating the variables. Putting all the y's on one side and all the x on, or all the n's on one side, all the t, whatever the output and the input variables are, you put all the functions on one side and all the inputs on the other side, and then you integrate both sides and then you solve for whatever your function is. But it's kind of getting a little ahead of ourselves here. We also like to talk about other things. For example, let's say that we have a population is growing according to the differential equation dn dt is equal to 1.3 times n times 1 minus n over 500. I will point out here, because I think it's important, when I write that n, I am thinking n of t, right? That n is a function of time. We don't write it that way because it's just cumbersome, but it's really, really good for you to think, oh yeah, that's really n as a function of time, so is that. Don't write that, but like know it. So here's what I want you to see. Well, no, we'll say that first. So first I want to find the equilibrium points, or the equilibria. Population sizes. So when we talk about equilibria, what that means is if the population happens to be that amount, it will stay that amount. Meaning it won't grow or decline. Meaning its rate of change should be, if you're not getting bigger or getting smaller, your amount of change is 0. Meaning the derivative should be 0. So the way you find equilibrium population sizes is by setting your derivative equal to 0. So set dn dt, which is equal to 1.3 times n times 1 minus n over 500 equal to 0. And in this case, it's relatively easy to see that either you're going to get n equal to 0, which makes sense, right? If your population is 0, it's kind of hard to grow more, right? Because you don't have any population to make more population. Or if your population is 500 here, if 500 over 500 is 1, 1 minus 1 is 0. This is an example of what's called carrying capacity. So here, this system can carry a population of 500, but if it gets to be more than that, well, let's say the population was 600. Well, the population was 600, then my rate of change would all of a sudden become negative, because 1.3 times 600 times 1 minus 600 over 500 is a negative number. So if your population gets too big, it's going to get forced back down towards that value of 500 because your rate of change is going to be negative. So these are the equilibrium values. Yeah. I want to say more about that. I kind of think I do. Yeah. Yeah, I like drawing this. So sure. So for what values of n is the population increasing? Well, the easiest way to do this is just to plot these things on an envelope. So we have our equilibrium values where n is neither increasing nor decreasing. So if n is equal to 0 or 500, the population is neither increasing nor decreasing. And actually, sorry. Yeah, sure. So if we pick a value of n larger than 500, well, we already talked about how, and I actually wanted to write dn dt here, sorry. So if n is bigger than 500, I should write this again because these pages are not going to be, let me write my derivative again, sorry. Or my differential equation again. dn dt equals 1.3 times n, 1 minus n over 500. Talked about before how if n is like 600, my rate of change is going to be negative here. And then if n is between 0 and 500, like say 100, well, that's positive, so the whole thing's positive. And then if n is negative, which might not always make sense to consider a negative population, but depending on the context, it might. So if n were to be negative here, you'd have a negative number times the positive number, so the whole thing would be negative. Which means that our population, n, is decreasing over here if the population is larger than 500, increasing over here if the population is between 0 and 500, and decreasing over here. So if your population starts off between 0 and 500, it's going to increase towards 500. If your population starts off bigger than 500, it's going to decrease back towards 500. And your population started off negative, it would decrease and get more negative. I don't love the way this picture looks, to be honest, because it's not very informative. Here's a better way of drawing this picture. What we're actually going to do is on our horizontal axis, we're going to talk about the value of n of t. Sorry, I can't really see that. And our vertical axis, we're going to talk about dn dt. So here's what we know. We know that between 0 and 500, dn dt is positive. So we've got something, let's just draw this in red. No, let's draw it in black. Let's draw it in blue. Kind of like that. Between 0 and 500, why did I put my 0 there? Right. Killing myself. Oh my God, it's terrible. I was like, I just want to. Terrible. Fine, I'm gonna fix it over here. I'll fix this later. Sorry, between 0 and 500, it looks like something like this. And then after 500, our dn dt is negative. I'll do this, man, this picture is not the best thing I've ever done in my life. And then over here, less than 0, it's also negative. So I'll just point out, up here is where dn dt is positive. I know we're out of time, almost. Down here, dn dt is negative. Okay, but here's what I want you to see. So if dn dt is positive between 0 and 500, that means n is increasing or decreasing. Right, so check this out. That means if I start here, I get pushed to the right. On the other hand, if n is bigger than 500, then n is decreasing, means getting pushed to the left. And then if we're over here, and if it makes sense to be over here, if n is less than 0, n is also decreasing. All right, check this out. 500 is a stable equilibrium because if you're a little bit of ways away from it, you get pushed back towards it. On the other hand, n equal to 0 is an unstable equilibrium. If you're a little bit away from 0, you get pushed away from it. That's all there really is to say there. And so often the question will be find the equilibrium of this differential equation and then classify whether they are stable or unstable. And you can do it in this graphical way that we just kind of showed in this example, or we'll talk about another way of doing that on Tuesday. So no, cobwebbing is not, it's not cobwebbing, no. No. But good question, because definitely cobwebbing was something we talked about. Cobwebbing is applicable for a slightly kind of different situation, but yeah.